Okay, notice that the thermometer is rising. Okay, there's 250 milliliters of mineral oil in there. Thermometer is rising. I'm agitating the oil. Now this thermometer is not on the resistor. It's measuring the temperature of the oil, not the resistor. Okay. And it's climbing, right? And here's, actually I have the oscillations turned down. This is the inline current. So you'd probably call that no measurable current from the battery. And what we have up here is the battery trace. This is the zero baseline right along here, the middle of the gradicle. And then this is the signal from the function generator, and it's, let's see if we've drifted off of its baseline. Yeah, we've drifted a little bit, so let me put that where it's supposed to be. And that's where it's supposed to be, so we'll turn the channels back on. And now what I'm going to do, I've got the function generator set to produce a triangle ramp, and the ramp is tilted over to the side. So I'm going to pull up the amplitude now. Let's make a note of this temperature first, okay? Because you can't get a reading on this thermometer while the oscillations are happening. It's too much RF. Okay, so we're still increasing in temperature there. I thought it had stabled out, but clearly it's not. We're still going up. Okay, let's call it 50.3. And that's it. A very, very small inline current, right? So now what I'm going to do is use the amplitude control of the function generator. And we'll turn it up and we'll get that. This is the gate signal. 5 volts per division, or rather, I'm sorry, 10 volts per division. 50 volts per division on the battery signal, and the time base is at 20 microseconds per division. So this is simulating the scope settings that are on screen 0243 of Ainsley's. All right. Okay. So you can see that what I've got is I've got a ramp signal into the gate. Okay. Now, we're still at a relatively low current. I want you to look at this little blip right there, that little blip right there as I turn up the amplitude, okay? Turning up the amplitude, notice that that blip, that little blip increases in size and moves to the right. And the gate drive, the peak of the gate drive tops off there. Now remember, this is a ramp, right? I'll show you the raw gate signal in a moment. But it's a ramp, a triangle or sawtooth ramp, okay? Now look what the current has done. All right. We've got an 1.5 amps going through the system now. We've got those nice spindly turnips, a little spike, a little chopped off top there, and then the oscillations on the negative part, the negative going part of the gate drive. And we're at 10 volts per division on that. So that's maybe 6 volts positive, something like that. But that's a very short time. The peak is going up in there. Okay, so now let's take a look at the temperature. Now remember, it was at 50 plus something, but I also cannot get a good temperature reading with this digital thermometer while the oscillations are happening. So what I'm going to do is turn them back down like this. All right, getting back to the sort of quiescent state with the ramp in there. A very small current in the series inline meter, and now the oscillations are not going to be affecting our thermometer anymore. Now, where is all that heat coming from? Is it coming from these little oscillations here? I don't think so. Let's take a look and see what those look like, if we can. Excuse me. Those are happening so fast. Oh man. Poor old oscilloscope just cannot keep up with those. Those are a lot higher than your normal oscillations that we normally see. So I'm just going to disregard those. Set that back to 20, and get our trigger back on those. That envelope. Okay, so what we're seeing here, I think, is the heat pulse that arose from the time when I had the big spindly oscillations on. These ones here, those, with that one in the middle, okay? Because that gives me a good high current, and that's happening because of the gate drive going high enough to turn the Q2 MOSFET on right in here, and then this is the spike from where the Q2 turns off. Watch, if I lower that ramp, see, if you can imagine just the peak of that ramp going over the voltage needed to turn the Q1 on, you can see that when the Q1 turns off, that's where that spike is, right? See that? What I'm doing is varying the amplitude, which is moving that peak up and down and causing that MOSFET to turn off at a little bit different time. Okay? And because the MOSFET is staying on at different times, I get increasing power with it like that on for the most amount of time, right? Or decreasing power as the peak of that triangle ramp turns the MOSFET on for less and less time. And where it turns off is indicated by this little spike right there. Okay, so as I vary that amplitude, you know, like that. Okay. Now, if I change the B channel to show not the battery voltage, but rather the voltage on the shunt, or the current sensing resistor, if I can get it off of there, off of this one. Okay. Put that there. And now, of course, we need to move back to our normal position and change the attenuation. Okay. So now what you're seeing, of course, is the voltage drop across the shunt at half a volt per division. Okay, half a volt per division. Now I'm going to do the same thing. This is the voltage drop across the shunt, half a volt per division. You can see that during the oscillations it's massively negative. But there's no, wait a minute, let's see here. Let's put that right back on its correct baseline, which is right there, right on the gradical marker, right there, okay. So you can see now that during the DC portion there's no current, right? It's right there. Now I'm going to turn up the gate drive again to push this peak up above the Q1 turn-on point. Look at there, okay. There's the Q1 turning on, there it's turning off. And look, the current is starting to rise, okay? Because this little part here is over the line, positive, but then looky here, we got that negative spike happening too. So let me keep on turning up the gate drive. This is the most up now. There's our 1.52 current again. So you can see that there's a substantial, remember our zero baseline on the current is that gradical marker right there. So there's a substantial positive current flowing in there. There's some bouncing back too, but that's not nearly as much as that positive current going on there. This spike though, here, the bandwidth of my oscilloscope is not sufficient to get it, but this spike is on a digital oscilloscope with high bandwidth. You'd be able to see that this spike goes way the hell down here, and that's where your negative power calculation is coming from. I'll bet you my hat that that's where it's coming from on this ramp stimulated type of signal. Okay, now let's see what that's doing to the load heat. So once again, I'm going to turn down the drive. Okay, and let's take a look at the true reading on that thermometer. Notice that it's still going up. That's because the resistor is so hot that it's heating up the water, even though right now there's very, very little current, 40 milliamps, flowing through the system. Alright, this is a heat pulse that was caused by the positive gate drive signal that I gave the thing half a minute ago. But right now there's very little current flowing through the load, yet the load is continuing to, or the temperature is continuing to rise because of the thermal mass involved in the 250 milliliters of mineral oil that's in there. Or in the nerd case, the large thermal mass of the big metal heating element that they're using. Okay, now you can see that it's kind of stabilized out, right? Okay, so now we'll go back over here and we'll give it another go. Sorry, allergies. Okay, so there, remember now, this is the current viewing resistor trace. This is the gate drive input, and we're sending a triangular ramp to the circuit. Okay, and there I've turned up the amplitude all the way. There we're chopped off from that triangular ramp. There is the resultant current turn on in Q1. There's a little bit of negative current, and then there's that big spike when Q1 actually turns off as this ramp drops below the threshold gate value of Q1. Okay, and we have a substantial current flowing. Now I'm fairly certain that this meter is doing a fairly good job of averaging the ripples that are on the battery. So you can believe it if you, or not. You know, I don't know. But right now it's showing that we have about, call it 50 volts times an amp and a half. What is that? 75 watts. So bump it down a little bit, so 70 watts or so, right? And believe me, 70 watts will heat up a load. And I can see that that wave shape is starting to get a little distorted in there, right? So what's happening here is, yeah, this MOSFET is getting warm. I can't tell you how warm it is because I forgot to hook up the thermometer to it, but I'm telling you, it's uncomfortable to hold. These are cold, okay? Now let's see if we can get a reading on the load temperature again, remembering that the oscillations are making the thermometer go crazy here. So let's turn off the oscillations. Confirm that we have almost no current flowing in the load, or from the battery, or however you want to say it. Now we agitate the oil and we look at the thermometer. Think we can get it up to 100 degrees if we do this a couple more times? Well, I've already wasted 14 minutes of your time, so I know that I can get this thing up to pretty high temperatures just by continuing to do this. And, oh, I promised to show you what the drive signal looked like without it being hooked up to the circuit. So well, you go ahead and just unhook it. Like that. And now this is the signal that we're using to drive the circuit just now. Okay. It's a ramp. It's tilted over as far as I could tilt it with my F43. I can get a true fast rise time ramp out of the old WaveTech, believe it or not, but this is as far as the F43 will go with this tilted ramp. Okay, thanks for watching.